Okay, hello everyone. This is Professor Lei. Let's continue to talk about chapter 10. All right, and this is part two of chapter 10. And in this video, we'll mainly talk about the quantitative methods of quality management. All right, and also we cover the Six Sigma approach. All right, we will briefly talk about the definition, the insight, and how we use Six Sigma approach in the quality management process. All right. And we already know that actually Six Sigma approach currently is widely used in different firms, different industries across the board. And we hope to introduce this approach and to help help firm do the quality management. All right. So before we jump to the calculation or statistical analysis related to Six Sigma approach, let's first talk about the insight or the core idea of Six Sigma approach. All right. As you can see within this slide, the Six Sigma approach basically can be viewed as a philosophy and a set of methods that the company use to eliminate, or more accurately, we can say monitor and reduce the probability of defective products in their production process and service process. Okay. And the core idea of using Six Sigma approach is very straightforward. We are trying to reduce the variation in this process that can lead to the defective products. Okay, you may wonder why the Six Sigma approach can help do that, can help achieve this goal. That's because first we know that Six Sigma approach itself is a statistical analysis, right? And the Sigma itself actually, since all of you guys already learn the business statistics, Sigma itself represents standard deviation, right, within the business statistics. Okay, so from a big picture point of view, by using Six Sigma approach, okay, you basically, if you are a firm, right, you produce a lot of products in your production line, all right, and each time you grab a sample all from all of your products, and then you do some statistical analysis, okay, based on statistical analysis, you can calculate your standard deviation, right? The standard deviation of the sample will reflect the variation of certain characteristic of this product. Okay, if the variation of certain characteristic, all right, let's say in terms of one aspect of the quality, okay, let's say if the length of this product is one aspect, right? If the variation of the length, okay, is within the range of within an acceptable range, then we say, okay, the quality of this product in this dimension is good. All right. But let's say if your product, the length of the product is already above a acceptable range, okay, that's actually set by your firm. You say, okay, this product right now probably have some problem, okay, in terms of this aspect of the quality. All right. Then we have to try to reduce the variation during this production process in order to reduce the number of defective processes in this process. Okay, so basically you have to figure out the reasoning behind and then try to fix this problem in order to reduce the variation in this process. But during this process, you can see Six Sigma approach as a very standard statistical analysis approach can help you to figure out and reduce the variation in this process. That's why we always use the Six Sigma approach in the quality management process. It's very important, all right? So why is it Six Sigma, not Five Sigma, nor not Four Sigma? Okay, this is actually based on the former experience, all right? So the reason that the Six Sigma approach basically, as I said, let's say for a product, right? The management may set up an acceptable range for, let's say, one dimension of the quality. Okay, let me give you an example. All right, if the length of the product that this firm is producing, the target is 10 inches. All right, but we know that even if it's made by a machine itself, all right, we cannot make sure that every unit of product is exactly 10 inches. Right, so instead of setting a target which is exactly 10 inches as a high quality product, in most cases, actually, they will set up a range. Let's say for this product, if it's between 9.95 and 10.05 inches, this is a good quality product. Okay, so if we set up this range for the firm, all right, and if in the production process, all right, let's grab some sample and calculate the standard deviation, all right. If this range can include the a total 6 sigma, all right, variation within this certain range, we say, okay, probably the quality of this product is already good enough. Okay, so what means by 6 sigma? So if we have a center point in the middle, there should have 3 sigma at the left hand side of the central point and have 3 sigma at the right hand side of the central point. That of course 6 sigma. But in total, basically, if this range that is designed by management can include 6 different sigma, okay, for this real production process, normally we say the quality of this product is good enough. Okay, so if I just describe like this, maybe it's a little bit abstract. Okay, but we will use the graph and use the real example to help illustrate. But here, just give you some sense about why Six Sigma approach is widely used to help increase the quality management, to improve it. All right, let's continue to do it. Okay, so Six Sigma approach is still following the philosophy of DMAIC procedure. Okay, which represents define, measure, analysis, improve, and control. Okay, we will detailedly talk about every term. Okay, just in the next slide. All right, but we should know that basically this Six Sigma approach is developed by the General Electrics. Okay, and right now it's used by many different firms. Okay, they're following this idea to help improve their quality during the production process. Okay, and yeah, so but for General Electric, okay, they firstly developed this in order to focus on efforts on quality using this methodological approach. Okay, and the core idea of this approach is still trying to, this core idea is still trying to focus on the customer needs. Okay, so we always say that as a firm, we first need to understand what is the customer need, and then in order to fit the customer need, we build up the quality criteria. All right, if we can well fit customer needs, we're saying that okay, the quality of this product is good. All right, so we always start from a customer, we build up the quality criteria to fit for the customer needs, and if we can do well for this quality criteria, we say this product is good. Okay, that's the core insight of the quality management. All right, we already mentioned that in the last video. Okay, I won't spend much time to talk about it. And as I said in the last slide, the Six Sigma approach by using the statistical analysis is to reduce the variation in this whole production process that may lead to the defective products. All right. So all we're doing basically just to reduce the variation. First, we monitor the variation and trying to figure out the reasoning behind it in order to reduce the variation in this process, in order to reduce the number of defective products, such that it will better fit for customer needs, right? By having a better quality products. Okay, so this is Six Sigma approach idea. Okay, now since we say that the Six Sigma approach is also following the philosophy of DMAIC, okay, we have to understand what is DMAIC, right? What it means by define. All right, since we always say that in order to build up a good quality product, we always start from a customer need, right? So define means that we first need to understand who is our customer, who are the customers, right? For this specific products, what are the needs? What do they need in terms of this product? Okay, that's the first thing. We have to define quality itself, right? But the quality is actually from the customer need. So we first need to understand who are the customers, what are their priority, what do they need from this product. Okay, in terms of that, we have a sense about, okay, what are the important quality dimensions for this product. All right, so this is the first one, define. And then we move to the second step, which is measure. Okay, once you understand what are the important quality dimensions, you basically you have to use different way, or um, an accurate way to measure this production process, measure different dimension of the quality, right? And yeah, so basically we have to kind of quantify the different dimension of the quality. Okay, so this is second step, measure. Okay, and once you measure the different dimensions of the quality process, all right, then we go to the third step, which is analyze. What it means by analyze, okay, um, based on your measurement, you probably already figure out the overall quality situation of this product. Okay, if it's pretty good, then you're good. But if it's not that good, all right, if the quality is barely acceptable, or on average is even unacceptable, all right, then you are getting into the analyze process, all right. So you have to kind of improve the overall quality situation. But in order to improve the quality situation, you have to first understand what are the important causes of these defective products. All right, what are the causes? Okay, so can we kind of monitor and even control all these different causes? Okay, in order to reduce the variation, reduce the number of defective products. Okay, that's a very important and a very important thing in order to improve the quality management. And actually, um, this process may actually take a lot of time, a lot of effort from different experts. All right. So once we figure out the most likely or a few different important causes of defective products, then we start to get into the fourth step, which is improve. All right. We're trying to, since we figure out, then we're trying to remove the causes of defective products. All right. We're trying to remove it. Okay. But even if you understand are the different causes of defective products, it doesn't mean that you can remove it automatically. Sometimes some causes of defective products may not be under your control, may not entirely under your control. Okay, and actually we have a lot of example about it. All right, and let's say if you can remove the cause of defective products based on firm's effort, and then we can get into the basically the fifth step, which is control step. Okay, the control step, right? Uh, Basically, in the control step, this step basically need you to maintain this improvement. All right, you don't want your improvement is like a one-shot improvement, right? You are trying to reduce the variation, reduce the number of defect products by your by your effort. All right, but the more important thing is to maintain this improvement during this process. Okay, such that the number of defective products is always below the limit that you set for this product. All right, so that's why actually the whole steps that I just mentioned, from define to measure to analyze to improve to control, this is a circle. This is a circle. This is a cycle. Means that this is not just a one shot approach, or um, one shot thing in order to improve your quality. All right, probably you have to kind of repeat this whole process, okay, many times during your production process, because no, not only the internal thing, internal reasons, but also the outside reasons are always changing, right? So your customers may change, your production process may actually getting affected by different reasons, all right? Such that the cost of defective products may change all the time, And in order to remove the different type of the cost of defective products, you have to spend much time, much effort during this process in order to improve or at least maintain the your quality management at an acceptable range. All right. So that's why this DMAIC is not a one-shot effort. It's actually um, it's a cycle. It's a cycle. Okay. So that's the core idea of Six Sigma approach. Okay. And we know that the Six Sigma approach itself, all right, is a statistical approach. Okay. So if we only use the statistical approach to help illustrate the quality management or help monitor the quality management, sometimes it's not that direct. All right. Even if we can get, let's say, the statistical, by using this statistical tool, we can use some analysis, get some report. It's a little bit abstract. All right. So that's why by using Six Sigma approach, in order to monitor the quality management in a big picture point of view, normally when we do Six Sigma approach, we will also use some data visualization approach to help illustrate the Six Sigma approach. Okay, that's why here in this slide, actually I list some of different analytical tools, or more specifically visualization tools, to help illustrate Six Sigma approach. All right, so it's all, you see that we include flowchart, run chart, Pareto chart, check sheet, cause and effect diagram, opportunity flow diagram, process control chart, all the different type of charts. Actually, every type of chart has its advantage when we deal with the quality management type of issue. All right, and I will talk about every different chart just in a second. Okay, right now, and but in this chapter, actually, we are more focusing on this different chart. We call it process control chart. Okay, so but let me briefly talk about these different charts one by one. All right. So the first one is called a flow chart. As you can see in this slide, all right, the flow chart basically records some important information during your production process. Okay. For example, your manufacturer. Okay. So it actually gives you help you record who actually input something within the production process in order to get something out, okay, and who is the customer, okay. So here you can see manufacturer, okay, use copier, okay, in order to copy some, let's say, some papers, and the customer is you, okay. This is a very simple process, right? This is just recording some events, basically, some events, all right, and like it shows in the bottom, okay, in the production process steps, okay, they say, okay, if you are trying to scan some paper, right, you put this original on the glass, and then you close the lid, adjust the settings, and press start, and then remove originals and the copies. Okay, so flowchart basically just recording the basic event during the production process. Okay, it's not that it's not that relevant to the core idea of the quality management, but at least it will record some important information related to quality management. You can use flowchart in your quality management as a setup, basically. All right. Now let's move to the run chart. Okay, run chart. So run chart, you can see that in the x-axis, all right, it represents from January, February, March until December. So basically here, the x-axis is basically the time, all right, from January to December. Okay, here the y-axis is representing the unit volume, all right. So in the quality management, you can use the defective products volume as the y-axis, all right. So let's say if this is not just the unit volume, but it's the defective product volume, all right, then you can say that, okay, so from the January, it's around 900. February, it increased to 1200, right? And if we follow this run chart by using this run chart, there's a very clear pattern here, right? It shows that actually the defective product starting from January actually is increasing until July. And then starting from July, it starts to decrease. Okay? So so based on the Six Sigma approach, right, we can do some specific statistics analysis. But if you can further use run chart to use run chart as we show here, you can very clearly see a pattern, right, within this chart. Okay, so basically from January to July is increasing, but starting from July to December it's decreasing. Okay, then you wonder why. It actually shows this pattern. Okay, it will actually help you to start thinking about whether the reason behind of having more and more defective in the first half of the year and then start to decrease in the second half of the year. Okay, is it because of some implementation? Okay, that you already you know you already set for the firm on the second half of the year, such that the defective products start to decrease, or is it because of some outside reasoning? Okay, so at least run chart will help you to kind of figure out, okay, how the defective product is changing during the um, season or during the along the time horizon. All right. Okay. Sorry. So then we move to the third one. Okay, it's called check sheet. Okay, check sheet is sometimes also very important. Okay, so here you see in this check sheet you list the different reasons. All right, so let's go back to quality management. If we try to use the check sheet within the quality management, right, you can first figure out some possible reasons of why we have defective products within the quality management. All right, so let's say you list out some of different reasons. All right, and each time when every unit have some problem, okay, after let's say after inspection or after test, you figure out the reason behind. Then you count, okay, you count the if this is because of, let's say if it's because of the barcoding, all right, then you count one unit here, all right, and in order to count the frequency of the defective products within different reasons, okay, that's actually very important because once you figure out the frequency of different reasons for the defective process, all right, then most likely, okay, the more frequent reasons is the more important reason that you have to figure out or you have to fix, right, in order to reduce the cost, reduce the number of defective products within the production process. Okay, so check sheet itself is also very important. It will help you figure out which reason probably is the most likely reason for defective products. And once you figure out which one is the most likely reason, you start to try to fix this problem in order to reduce the defective products and save cost for your firm. Okay. So next one is the cause and effect diagram. All right. So cause and effect diagram, we also call it fishbone diagram. Okay. So the cause and effect diagram is a little bit similar as the check sheet, but it's still have some difference. All right. So here in this slide, let's say finally we are trying to figure out the late pizza delivery on Friday and Saturdays. Okay, let's show you right here. We're trying to figure out the reason why we have this kind of situation. All right. So the reason can have four different broad source. Okay, it can be some equipment reason. It can be some people reason. It can be the method reason, or it can be the material reason. Okay, so basically it has some four different type of reasons. Okay, and under each reason, all right. Okay, so you may also have some very more specific reason under this category. All right, that's why here, let's say if it's under people reason, all right, it may be it's because the driver get lost, or because people actually don't show up, all right, such that the pizza delivery is late on that day. Okay, and why the driver get lost or why people don't show up, it may have the more detailed reason. So that's why you see actually the cause and effect becoming more and more specific and more details within this cause and effect diagram. Okay, so it will also help you to figure out what is the underlying or what is the fundamental reason of having defective products within this process. So that's why cost and effective diagram is also important, because it will help you to explore the basic and the fundamental reasoning behind. All right. The next one is opportunity flow diagram. All right. The opportunity flow diagram, basically, the inside of using opportunity flow diagram is to provide you the whole procedure of the production process. Okay, we can view this whole thing as the detailed um, procedure of the production process of producing this product. All right, so based on this whole thing, you can figure out which step normally will have the problem, which step have the problem. All right, and that would be the step that you have to more focus on. Okay, why we always have the problem with this specific step, and most of the defect projects is because of the step. Okay, then once you can figure out the reasoning behind, actually it will be much it will be actually you will become more and more productive. All right, but normally when we use opportunity flow diagram, we will use let's say check sheet or cause effect diagram simultaneously. All right, because opportunity flow diagram itself actually will give you the sequential procedure. All right, and if you can use the opportunity flow diagram with the cause and effect diagram or check sheet, that will be help you to basically the underlying reason of using all the different diagram is to help you explore the underlying reason of the defective products. All right, so sometimes we use some of those diagrams simultaneously. Okay, now let's get to the process control chart. Okay, so process control chart is actually very important, and to be honest, almost all of the status analysis, okay, will also accompany with the process control chart in this chapter. Okay, we'll mostly talk about the process. We'll mostly use the process control chart when we do the status analysis just in a second. Okay, so let me give you a detailed explanation about what is the process control chart. Okay, so process control chart actually is very simple. All right, so you can see that actually in the process control chart, there are three different things. Okay, besides the real data. All right, so basically in the process control chart, we have the UCL and LCL. Okay, the UCL basically is the upper control limit. The LCL basically is the lower control limit. All right. So basically, upper control limit, lower control limit is very straightforward. They are basically the upper bound and the lower bound of this control chart. Okay. We will talk about how to calculate the upper bound and the lower bound of this process control chart. Okay, just in a second. But in the process control chart, you have the upper bound, you have the lower bound, and we record the upper control limit and lower control limit. That's it. All right, and you see that in the middle there's a solid line. This solid line basically is the central point. Okay, it's at the middle of the upper bound, upper control limit, and the lower control limit. Okay, so this is the middle line. All right, so basically within this control chart, you have three lines. All right, upper control limit, middle line, and lower control limit. That's it. The specific points showing here, all right, is based on the real sample data. Okay, it's based on real sample data. Let me give you an example to illustrate. Let's say for your firm, you produce products, okay, let's say every day, all right? And let's say you produce 100 products every day, okay? You produce 100 products every day. And within this 100 products, you always grab 10 and make up as a sample, all right? And if we go back to the example that I just mentioned, okay, so if we are trying to measure the length of every unit of product, okay, length of every unit of product, okay, so then basically we can record the unit of, you can record the length for every unit, right? And since in your sample you have 10 different units, okay, you can calculate the average length of the unit within the sample, okay? And you can see, let's say the target is 60 inches, is 60 inches. Okay, in the first day, okay, the average of the length of the 10 different units within your sample is, let's say, is 90. Okay, in the second day, within another sample, including another 10 units, the average is around 65. Okay, the third day, the average of length of the 10 different units, okay, is around 75. Okay, so you can see this is fluctuating every day. It's fluctuating every day. Okay, and if you look at the whole pattern, right, it seems that this pattern is kind of random. Okay, you cannot actually find out any pattern here. Okay, any specific pattern here. Yeah. So and all the different dots within this chart is within this upper control limit and lower control limit. Okay. So that's actually, do you think that's a good thing or bad thing? Of course, it's a good thing, right? If we design the upper control limit and the lower control limit, if every dot is within this range, it means that, okay, so on average, all right, the thing that you are measuring is acceptable because it's within this range, all right? Let's say if one dot is already above the upper control limit or below the lower control limit, that's not good. That's not a good thing, right? That's actually very intuitive. It's not a good thing. Okay, here is a good thing, okay? But let me ask you another question, all right? So let's say if you're looking at this pattern, and this pattern is totally random, you cannot figure out any specific insight within by just looking at this pattern, right? It's not like it's always increasing, or it's not like it's always decreasing, right? It looks like it's random. Is it a good signal or bad signal in terms of the quality control? Think about that. Actually, if it's random, okay, it means that, okay, so the reason that actually we have the variation, okay, let's say if the target is exactly 60, okay, but you already figure out that it's not exactly 60 for every sample, right? Because it's sometimes above, sometimes it's below this 60 line, right? It means that it actually has some fluctuation during this process, although on average it's between UCL and LCL, okay? So if this pattern cannot show some, some insight during this process, okay, actually it's good and it's also bad. Okay, it's a little bit tricky. It's good because since this is random, right? All of the variation within this pattern probably is called random variation. Basically, these are the variation you may not be able to control. You may not be able to control. Okay, the reason that I say it's also bad because, okay, since this is random, right? It's not like it's always decreasing or it's always increasing, right? If it's always increasing or it's always decreasing, actually, that would be good in terms of figuring out the underlying reasoning, right? Because if you can figure out the underlying reasoning, it actually indicates that you can reduce the number of defective products, right? And in order to improve your quality management level. But here, since it's always random, it would be hard for you to figure out the underlying reasoning. All right, so it's bad in terms of improving quality management because it's harder for you to figure out the underlying reasoning of your defective products. Okay, so this is the brief introduction of the process control chart, and we will use this process control chart very frequently in our statistics analysis just in a second. All right. So here in this slide, we also mentioned these two different additional Six Sigma tools, which are fair mode and effective analysis, and also the design of the experiments. Okay, we're not mainly talking about these two things. But if you are interested, please look at the page 316. All right. So I give you some description about this two Six Sigma approach. But we will not use these two different visualized approach in our quality management. All right. Okay, so now we will start to talk about the statistical analysis itself. All right. So this statistical quality control procedure, all All right. Of course, this is the quantitative aspect of our quality management. Okay, based on the Six Sigma approach. All right. Of course, we know that no matter it's the production process or the service process, all right, you usually will exhibit some variation in their output. Okay, and the status analysis or the Six Sigma approach itself is trying to monitor and further reduce the variation in their process in order to decrease the number of defectives in this process, right? That's our target. All right. But sometimes the variation, normally the variation has two parts, okay? We name it as the assignable variation or the common variation, okay? So actually the difference between assignable variation and a common variation is actually very straightforward, okay? What it means by assignable variation? Normally, when the variation itself, if you can figure out the reason of this variation, okay? So basically, if the variation is caused by some factors that you can figure it out or you can manage it, we view it as an assignable variation, okay? We view it as an assignable variation. But so on the other side, if you cannot actually figure out what is the reason behind. Actually, let's say if this variation is inherent in the process itself and you cannot get rid of it, then we say, okay, this is the common variation. Okay, so let me ask you a quick question. In terms of increasing the quality management, all right, you should more focus on the assignable variation or the common variation. All right. Of course, we should more focus on the assignable variation. Why? Because since the assignable variation, you can figure out the underlying reasoning, right? Then you can should think about which way we can basically, in order to fix this problem, which way we can do in order to reduce this assignable variation, such that the number of defective products will decrease and the quality management level will be increasing, right? So we're more focused on assignable variation during the production process. Okay. Now, measuring variation, yes. So this is basically just a recap of business statistic things. All right, let me give you a quick sense about it. All right. Although actually, I trust all of you guys that you already learn and know how to do these two different things. So when we measure the variation, we need to know two different things. All right. So the first one is basically the mean. Right. The second one is the standard deviation. Okay. I think this is very straightforward. First of all, for mean, okay, why we normally calculate mean in the statistics analysis? Because mean itself is a very standard measurement of central location, right? It's a very standard measurement of central location. Okay, so let's say we grab a sample with 50 different points. If we want to get the mean of it, it's very simple. So you get the number for every unit, and then you add all them up, and then divide by 50. That will give you the central point, which is mean, right? Which is mean. And then the standard deviation is another measurement. Okay, instead of measure the central point, the standard deviation basically measures the dispersion, okay, within your sample, right? The dispersion within your sample. Okay, so what you can do basically by following the formula right here, all right? Since you are trying to measure how much individual observation deviate from the mean, right? Then basically you first have to calculate mean, right? You still need to calculate mean, and then use every individual observation minus the mean and take the square, okay? And add all those different numbers, add all them up, divide by n, and then take the square root of it in order to get the standard deviation. Okay, that's a very standard statistical process. This very standard statistical process to measure the dispersion within your sample. Okay, I think I don't need actually spend too much time to talk about this, since all of you guys should know it in business statistics course. Okay. Okay. Now, these are two important concepts. All right, the concept within the Six Sigma approach or the statistics analysis approach. All right, so let me give you a quick sense about it. Okay, actually it's very simple. All right, so let's say for a firm, all right, go back to the example that I just illustrated. Let's say for your firm, you're producing a product, all right, and your target of the length of this product is 10 inches. But we always know that even if it's automated by the machine, okay, instead of having any labors doing this process, okay, your product, okay, every unit of the product may not be exactly 10 inches. Sometimes it can be a little bit higher, sometimes it can be a little bit lower, right? But for the management, you have to decide, okay, in what extent, okay, if it's above or it's below our target, which is 10 inches, is still acceptable, right? So sometimes, let's say for your firm, you finally decide, okay, instead of asking every unit of the product is 10 inches, if this product is between 9.95 and 10.05 inches, we think this is still acceptable product, right? So instead of having a point requirement, you're actually having a range requirement, right? So in this example, the 10.05 inches is actually the upper specification limit, which is exactly the thing that we mentioned here. Upper specification limit, okay, which is the maximum acceptable value for a characteristic, okay? And on the other hand, the 9.95 inches in that example basically is corresponding to the lower specification limit, okay? It's corresponding to lower specification limit, which is the minimum acceptable value for a characteristic, all right? So, yeah. So this is how we basically build up the specification limit, right? So specification limit, in a sense, basically is the requirement, all right? The specification limit is the requirement designed by the firm, okay? It's designed by the firm, all right? So normally, only if this product is within this range, you think this is acceptable. If this product is not within this range, it's not acceptable, all right? So this is about a specification limit, or more specifically, upper specification limit and lower specification limit, okay? So here I also list two different views. The traditional view of the specification limit and the Taguchi view of the specification limit, all right? We will not focus on the difference of these two things, but let me give you a brief explanation about what is the difference between these two things, all right? In the traditional view of the specification limit, okay, let's say if your length of this product is 10.04, okay, inches, then we say, okay, this is acceptable because 10.04 is still within the range between 9.95 and 10.05, right? But let's say if this product is 10.06, then suddenly we view this product is unacceptable because 10.06 is above 10.05. Okay, so in traditional view, only if the product is within this range is actually acceptable. If it's above this range or below this range, it's unacceptable. Okay, but what is the Taguchi view on the right hand side? Okay, it makes the so core idea is that it makes the discrete range. Okay, it changes the discrete range and to a continuous range, What it means, okay, to a continuous range. It means that actually, since our target of this product is exactly 10 inches, okay, and in Taguchi's view, okay, we view that if the difference of the length of this unit is if the difference between the length of this exact unit and our target is smaller, then the quality of this product is higher. Okay, so you see, if this point, if the let's look at this picture, all right. If the product, okay, if the length is here, okay, instead of here, okay, you can see that actually the quality at this point is higher, is basically the quality here is higher than the quality here because it's more closer to your target, right? So basically the Taguchi view makes everything continuous instead of discrete, okay? But that's not the main point, and that's not the main point of this chapter. But actually, by using Taguchi view, you also have this problem because although in the traditional view, actually many firms, a lot of firms still using the traditional view because sometimes it's not that intuitive, but it's still it's very straightforward, right? although we actually view every unit within this within this range is acceptable with no difference, right? Basically, every unit within this range is actually having no difference. All right, but it's sometimes not that intuitive, right? But actually, it gives you the hard specification limit. It's a hard limit, right? But here it's continuous. It becomes more intuitive because if this product is more closer to the target, it's actually having a higher quality. But since this is not having a hard rule or hard space, then sometimes how we define whether this is acceptable or not is becoming more difficult. That's why it also has its own problem. All right. Okay. Now we come to the process capability. Okay. So yeah. So the process capability basically is your ability of within your process procedure to consistently produce a good or deliver service with a low probability of generating a defect. All right, a defect. Okay, and we already talked about the specification limit, right? The specification limit is a range of variation that is considered acceptable by the designer or the customer. Okay, so the core idea of a specification limit is basically this is a range of variation, and this is designed by your manager or by the customer. Okay, so this is your basically this is your plane. This is your plane. You hope that in the production process that the unit is within this range. All right, but here actually we have another limit, which is called process limit. Okay, so you guys have to clearly understand what is the difference between specification limit and process limit. Let me give you some sense about what is a process limit. The process limit, first of all, is a range of variation that a process is able to maintain with a high degree of certainty. Okay, but the core idea of the process limit, all right, process limit is not designed by your manager or by the customer. All right, process limit is based on the real production process. Okay, it's based on real production process. Okay, specification limit is a plane. Okay, it's a plane. It's a range of variation that is basically preset by your manager or customer. All right, but the process limit is based on the real production situation. Okay, it's a real production situation. It's still a range of variation. Okay, it's a still range of variation, but it's based on the real production process. Okay, such that in the process limits you have the central point, which is mean, and also you include the standard deviation to basically reflect the fluctuation within your production process. Okay, but of course the specification limit, although the specification limit and the process limit are different things. All right, are different things, but they can compare with each other. All right. So let me ask you guys a question. So if the process limit is outside the specification limits, which means that, let's say if the fluctuation or the variation within the real production process is actually bigger than your plane, do you think this is a good thing or bad thing in terms of quality? Of course, it's a bad thing, right? Because basically your real production process cannot fit for your plane, right? The variation itself or the fluctuation itself is already above your plane, is bigger than your plane, then this is not a good thing. Okay. On the other hand, if the process limit is within the specification limit, then you can say, okay, probably this is a good thing because you already limit your variation relatively small, such that you're already within your specification limit, which is basically your plane, right? Then it's good in terms of quality. Okay. We will build up specification limit and also build a process limit, and we'll compare these two different things in our static analysis just in a second. But here, it's very important to figure out what is the specification limit, what is the process limit, what are the difference. Okay, then we move on. Okay, so here, this is basically just a graph point of view to help illustrate the difference between specification limit and process limit. Okay, let me give you a quick recap of it. All right, so let's say your target, all right, is the target for the length of this product is 1.25. That's why the central point is 1.25. All right. But as a manager, you clearly understand that for every unit, it cannot be exactly 1.25, even if it's made by the machine. All right. So even before the production process, you can set up a limit, or you can set up a range. Okay. That you hope that the production can fit in, right? And you can tell your employee that we hope that this product, the length of product is 1.25, but you can have a 0.0 let's say 0.005 error in both direction. All right. What means by having error of 0.005 in both direction? It means that although our target is 1.25 inches, right? But let's say if your error is within 0.005 in both, in both direction, it's still acceptable. Okay. So based on this information, you can build up the specification limit, right? So our target is 1.250, all right? But if it's less than 0.005 inches above, which is basically corresponding to 1.250 plus 0.005, which is 1.255, is still acceptable, right? Or on the other direction, if you use 1.25 minus 0.005 to get the 1.245, you also, good for the quality dimension. All right. So you see that actually when I do this calculation, right, when you use 1.25 plus 0.05, you are getting the upper specification limit. That's right, the upper specification limit. All right. But if you're using 1.25 minus 0.05, it's 1.245. Basically, you are building up the lower specification limit. All right. So in terms of the essential point, all right, and in terms of the error that you can accept, you build up both the lower specification limit and upper specification limit. So the lower specification and upper specification limit basically compromise the range that you can accept. Okay, even before the production. All right. So this is the specification limit. Okay. Now let's say the real production process starts, okay? And you start to produce some product. And based on the real products that you already produced, let's say you grab an example, all right? And you calculate mean. Let's say the mean of these all different products is still 1.25. It's still 1.25, okay? That's good, because the mean is corresponding to the target that you have, all right? But on the mean, on the same time, all right, you can also calculate what is the variation during this process, right? Because even though the mean is 1.25, it doesn't mean that every unit is 1.25. It can be above, it can be below 1.25. Okay, but when you calculate the mean, you just compensate with each other. That's why your mean is 1.25, right? So when we calculate the variation, basically you're trying to calculate the standard deviation. Okay, you're trying to calculate standard deviation. Okay, and since we are using the Six Sigma approach, the central point is 1.250, okay? So we use 1.25. Let's say in the real production process, since the mean is 1.250, all right? In order to get your upper process control limit, how you do that? You use 1.250, which is your mean, plus 3 sigma, okay? Okay. So in this example, if we assume that we figure out that the standard deviation, based on the calculation, if we figure out that the standard deviation is 0.002, all right, and if we are trying to find the upper process control limit, you just use the 1.250 plus 3 times the sigma, which is 0.002, all right. So 1.250 plus 3 times 0.002 is 1.256. So 1.256 is corresponding to the upper process control limit. How to build up the lower process control limit? Very simple. 1.250 minus the 3 times 0.002, which is 1.244. Okay? So by following this way, you already got the lower process control limit and upper process control limit, right? It's actually very intuitive. Why you use 1.25 plus or minus 3 times the standard deviation? because you are using the Six Sigma approach, right? The Six Sigma approach is in two different dimensions, right? The left-hand side, right-hand side, right? So that's why here, since the whole thing includes Six Sigma, half of it actually includes Three Sigma. That's why we use plus or minus 3 times the sigma, okay? 3 times the sigma. So you make sure that overall it actually includes 6 different sigma, 6 sigma, all right? Okay, so we know that the specification limit is 1.245 to 1.255. But the process control limit is actually from 1.244 to 1.256. Do you think this process is good enough or not? Based on what we just mentioned, all right, since the process control limit is actually already bigger than the specification limit, all right, it indicates that, okay, it's not good enough, all right? You have to kind of try to figure out the reasoning of, of this high variation, all right, and start to fix the problem and try to reduce the variation such that the process control limit is within the specification limit, okay? But right now, this whole production process is not good enough. Your quality is not acceptable. It's not acceptable, all right? Now let's say, okay, by figuring out the reasoning behind, we already reduced the variation during the process, all right? You see that originally the production process is between 1.244 to 1.256. Now let's suppose that we already figure out the problem and figure out the reasoning and fix the problem, and such that the variation during your production process becomes much smaller, okay? And we figure out, okay, if we grab the example, we grab a sample, and we figure out, okay, the mean is still 1.250, but the standard deviation is becoming much smaller. So you use the 1.250 plus 3 times the smaller sigma, okay? Times smaller sigma. And then you use the 1.250 minus the 3 times the smaller sigma. That's how you get this green curve. That's how you get this green curve. And this time, you see this green curve is entirely within the range of 1.245 and 1.255. That's the point. That's the point, all right? So here, by improving this process, you figure out, okay, since the new process control limit is within the specification limit, right? So that means that, okay, it's good. Your quality is already acceptable, all right? Okay, here, in order to figure out how well, okay, the process control limit is fits within the specification limit, we use a very important index. We call it process capability index, okay? The process capability index. Actually, this index is very important, all right? But actually, it's very straightforward. Okay, let's talk about this, all right? So first of all, what is the process capability index? It's a ratio of the range of value produced divided by the range of value allowed, okay? The range of value produced basically is corresponding to the is corresponding to the process control limit. The range of the value allowed basically is corresponding to the specification limit. Okay, you're using the ratio of the range of value produced divided by the range of value allowed. The reason behind, basically, you are trying to show how well the parts being produced fit into the range specified by the design specifications, right? How well it fits in, how well the real production process fits in your plane, your design specifications, okay? And then normally we say, okay, after calculation, okay, here we have the formula, right? We have the formula. Basically, we have basic CPK is the minimum number between these two different things, all right? X double bar is the mean of the process, real production process. This is X double bar. LSL basically is the lower specification limit. USL is the upper specification limit, and the sigma is the standard deviation. So basically, okay, in these two parts, the X double bar itself and sigma itself is from your real production process. Okay, the LSL and both LSL and USL is from your design. Okay, it's from your specification design. All right, and once you get all these numbers, you plug in you figure out the corresponding result, all right, and then you calculate the mean between these two different numbers to get the CPK, all right. So if the CPK is larger than 1, it actually indicates that the process itself is capable, is good, okay. And when the CPK is larger, it means that your process is better, okay. So the larger number of CPK is corresponding to a better process capability, okay. Yes. So yeah, that's a very important point, right? When the CPK is larger, it represents a better process control procedure, okay. And if it's larger than 1, it already indicates that it's already very good, okay. Let me give you an example to help illustrate this process, okay. This example is very straightforward. Suppose that the diameter of the bearing is set at 1.25 inches plus or minus 0.005 inches, which indicates that, okay, since actually you are trying to set at 1.25, that's your target. But if it's plus or minus 0.005 inches, it's acceptable. So based on this information, we can automatically figure out the upper specification limit and lower specification limit. Right here, I already tell you, right? But you can simply calculate yourself. The upper specification limit is just 1.250 plus 0.005. And the lower specification limit is just 1.250 minus 0.05. All right. So in order to get this 1.255 and 1.245. All right. And if in actual production process, the sample shows that the mean of diameter of the BRA is 1.251 inches and the standard deviation is 0.00083. Okay. So which indicates, okay, so this sentence basically is corresponding to the information related to the actual production process, right? The actual production process. And if based on the sample, the mean of diameter is 1.251, which indicates what? It's corresponding to which notation? X double bar. Okay, so X double bar is 1.25 inches, and the standard deviation is 0.00083, which is corresponding to sigma within this notation, within this formula. All right. So actually, this example is very straightforward, right? So as long as you know exactly what every number means, you just plug into this equation, all right, to calculate capability index, right? Yes. So basically, the X double bar is 1.2551 minus LSL is 1.245 divided by 3 times the sigma, which is 0.00083, in order to get this number, which is 2.4. And by following the same fashion, you can get another number, which is 1.6. But since we know that the capability index is corresponding to the minimum number between these two, basically, what is the result? The result is 1.6, because 1.6 is less than 2.4. So the capability index of this production process is 1.6. Okay, if I ask you by getting the capability index, all right, is it a good index or bad index in terms of the production process? It's good. Why? Because the rule of thumb is that when the CPK is above 1, it's already good enough. Since it's 1.6, it's good. Okay, it's already acceptable. Okay, so this would be the first question. But let me ask you another question. What is the probability of producing a defective product? Okay, the probability of producing defective product. All right, how to get this number? Actually, we may have, since all of you guys already learned business statistics course, actually, it not be hard for you to get this number. But let me give you a recap of it. All right. So let's say if we are trying to guess we're trying to guess the probability of having defective products, right? And if you look at this whole curve, all right. Okay, if the specification limit is like this, ignore the specific number here, okay, because the number is different. Here, if the specification limit is here, okay, and if the process control limit is like this, okay, which area is corresponding to the area that's actually producing defective products? What is it? What are the areas? It's this yellow area plus this yellow area. Okay, so basically these two areas, or the sum of these two areas, are corresponding to the probability of having defective products. Okay, But how to measure these two areas? Okay, this is actually very simple, just using the z-table, right? But before we can use z-table, we have to figure out, okay, what is the specific z-value? What is the specific z-value? Okay, right here and also right here. Okay, right here and right here. Okay, how to get these two numbers? I already showed here, right? In order to get the z at the left-hand side, you can use LSL minus x double bar divided by sigma. That's it. In order to get the upper specification limit, you use USL minus x double bar divided by sigma. Okay, so here when you use this equation, okay, be careful. These two equations, okay, is similar as this equation when we calculate process capability index, but it's different. What is the difference? Here, when you count the z value, okay, no matter LSL and USL, you always use LSL minus x double bar or USL minus x double bar. Okay, it's different for the sequence right here in the numerator. You see, okay. But when we talk about when we calculate z value, you always use the corresponding lower specification limit minus x double bar or upper specification limit minus x double bar divided by sigma. Okay, so this is the z value. All right. Once you get the z value, how to get the probability of that? Remember, how to get the probability? You check the z-table, right? But a very important thing is that when you check z-table, right? When you check the z-table, z-table will only give you what? Z-table will only give you the probability of z which is less than or equals to some specific value, right? Remember that's with the B-stat course, right? So the z-table always gives you the probability of z which is less than or equals to some certain value, all right? So once you get these two numbers, basically these two z values here, you can use the table to simply guess the area here, okay? Because this is the probability of z which is less than or equals to some value, right? But based on this value, if you use the table, what is the area that you get? The area is simply the whole area, okay? At the left hand side of this number, But what is exactly the area that you want? It's at the right hand side of this number, right? But how to get the right hand side number? You can use 1 minus the whole area to the left hand side of this number to get this yellow area. And once you get this area and you get this area, you add them up. That's why here, okay, we always use the probability of the z which is less than or equals to this smaller number, but plus the 1 minus the probability of z which is less than or equals to this bigger number. Okay, and the intuition is exactly what I just mentioned.